Hi everyone, and welcome back to the video series on the Ornstein-Uhlenbeck process. In today's video, I will show how to simulate the process in Python using two different methods. As a reminder, the Ornstein-Uhlenbeck process is a Gaussian process defined through a stochastic differential equation. The first term on the right-hand side tends to bring x back to its average value mu, while the second term provides stochastic driving. The joint action of these two terms results in a stationary process that has a finite variance. The one-dimensional Ornstein-Uhlenbeck process considered here is sufficiently simple and allows for a closed-form analytical solution. If at time 0 the process has value x0, then its value at a later time t will have a Gaussian distribution fully specified by its mean and the variance. We will use this analytical results in simulating the process. Specifically, given the initial state x0 and the step size delta t, we compute the mean and the variance of x at time delta t and sample it from a normal distribution. Then the sampled x delta t is used as an initial state to sample the process value at the next time step. This procedure is repeated multiple times until the desired trajectory duration is achieved. Now let's go over the code that implements this in Python. First, we import the library NumPy to perform various mathematical operations and the pyplot module of matplotlib for making graphs. Next, we define the three parameters of the process and introduce tau as the characteristic timescale. We then specify the initial state x0, the time step delta t, and the total duration of the trajectory. In this case, I set delta t to be a small fraction of the characteristic timescale so that the trajectory captures fast dynamical features of the process. And the total trajectory duration is set to be an order of magnitude larger than tau so that the process manages to relax from its initial state. Having defined all the constants, we proceed to trajectory simulation. We initialize a NumPy array for the process values, setting the first value equal to x0. We also define an array for equally spaced times. Then we iterate in a for loop, and at each iteration implement the procedure described earlier. Specifically, we treat the latest x value as initial state, compute the mean and the variance of the next x value, and sample the next x value from a normal distribution using a built-in NumPy function. After sampling, we store the value. This is essentially all the code needed to simulate the process. Once the trajectory data is generated, we can plot it in a figure. Here you can observe the stochastic regression of the process towards the mean value mu on a timescale of a few tau, after which the contribution of the initial state on the dynamics becomes vanishingly small. For reference, we can also highlight regions that are 1 and 2 standard deviations away from the average dynamics. They help distinguish the initial transient phase from the stationary phase. At the end, I'll briefly talk about simulating the process using an alternative numerical integration method, namely the Euler-Maruyama method. The Euler-Maruyama method is an approximate procedure for numerically solving stochastic differential equations, without requiring the presence of an analytical solution. When applied to the Ornstein-Uhlenbeck process, it obtains the next x value by advancing the deterministic part evaluated at time t and adding an independent Gaussian noise that depends only on the parameter sigma and the time step delta t. This update rule is in fact the order delta t approximation of the exact update rule discussed earlier. To implement it in Python, all we need to do is to use the approximate equations for the mean and the variance at each iteration. Everything else remains the same. Since the method is approximate, the statistics of the generated trajectories will be different from the exact results. To see how the choice of the time step affects the accuracy, we compute the relative error in the standard deviation for different choices of delta t. As shown in the graph, the standard deviation is overestimated, and its relative error grows linearly with delta t. However, if the step size is chosen to be an order of magnitude smaller than the characteristic timescale tau, the error will be only a few %, which is sufficiently low for many practical applications. As you can see, simulating the Ornstein-Uhlenbeck process isn't hard and can be done in a few lines of code. With the simulation method at hand, you can scale it up to very large sample sizes and numerically explore more advanced statistical properties. That will be the theme of my upcoming video, so stay tuned.